Welcome to aminacademy.com. In strength of material, let us discuss about effective or equivalent length of column. The effective length of a given column with given end conditions is the length of an equivalent column of the same material and cross section with hinged ends, and having the value of crippling load equal that of the given column. Effective length is also called the equivalent length. That means you have to calculate the equivalent length or effective length of the column by using the end conditions of the column as hinged both sides. Here, we'll discuss further. Let LE equals effective length. Effective length of column, and L equal actual length of the column. Actual then crippling load. Crippling load for any type of the column with end condition is given by with end conditions given end condition, that P equal pi squared E L over I over LE square, where L equal to effective length, E equal to young's modulus, I is moment of inertia. The crippling load P in terms of the actual length and effective length also the relation between effective length and actual length is are given in the table as follows. That you have the table here. End condition: first, both ends are hinged. Are there? Look at here. Both ends are hinged. The actual length is pi square EI over L square. Effective length is pi square EI over effective length square. Then here the relation between effective length and actual length is L equal to length of the column is equal to effective length. That means both are same formula. Now one end is fixed and other end is free. Then here crippling load is pi squared EI over 4L squared. Then here pi squared EI over LE square, where here LE equal to 2L. Next, third, both ends fixed is 4 pi square EI over L square. Here pi squared EI over effective length square. The comparison of LE equal L by 2. Next, here one end is fixed and other end is hinged. Here the crippling load is 4 pi squared EI over 4 pi square EI by L square. Now we'll check this. Both and flexure is equal. The 2 pi square, not 4. 2 pi square. Here pi square EI over LE square. Here the condition is LE equal L by root 2. These are the conditions for effective length and equivalent length. Effective length and actual length of the column. Now crippling stress in terms of effective length and radius of gyration we'll discuss. Crippling stress in terms of effective length and radius of gyration. Here we know that I, moment of inertia, equal A k square, where A is area of cross section and I is the least value of moment of inertia, then k is the least radius of gyration. Then P, crippling load equal pi squared E into A over LE squared in terms of area under, because in terms instead of I you are using this AK square, equal pi squared E and AK square, this I here, I is AK square over LE square. Now further we can write this as, look at here, pi squared E A over LE by K the whole square, and the stress corresponding to the crippling load, crippling stress is crippling load by area, P over A is equal, P is already pi squared E over LE by K the whole square by A, which is equal pi squared E over into A here, thus both A cut, pi squared E over LE by K the whole square, where this LE by K is slenderness ratio that we will discuss here. Next is slenderness ratio. The ratio of the actual length of the column to the least radius of gyration of the column is called a slenderness ratio. Therefore, you can write which is equal actual length actual length of the column over least radius of gyration equal L by K. This L by K is called a slenderness ratio. Now, next is limitation of Euler's formula. Look at this. Here, the crippling stress. We know that crippling stress is, we know that y squared e over Le by K the square. For the column with both ends hinged, for example, for column both ends hinged is, we know that for this Le equal to effective length is equal to actual length, hence crippling load. Hence crippling load is y squared E over L by K the square, where L by K is the slenderness ratio. Now, if the slenderness ratio, that is L by K, is small, the crippling stress for stress at failure, that is the crippling stress, will be high. But the column material, the crippling stress cannot be greater than the crushing stress. That is load when failure. Failure of the column is called a crushing stress. Hence, when the slenderness ratio is less than the certain limit, that is Euler's formula gives a value of crippling stress greater than the crushing stress. For safe load, crippling stress is great. Crippling stress equal crippling stress is greater than the crushing stress. It should be greater than the crushing stress. So far we discussed about the tabular form of different condition of load, as well as crippling load and actual length and effective length, and comparison of actual length and effective length. And as well we discussed about crippling load of in different conditions. We have done. Please subscribe our YouTube channel.